Hello everyone and welcome to my YouTube channel. My name is Subhashish Mishra and today's topic of discussion is on principal component analysis practical implementation using Python. Before we start, if you are new to my channel, please subscribe, like and share and also turn on the notification bell so that whenever any new video gets uploaded you will be notified. Alright, so the first thing we need to know before implementing it practically, what exactly is a principal component analysis? So in any given data set, as we know, if we have more dimensions or features, then we always have to we always have the threat of the curse of dimensionality, because as we have more number of features, then there will be a higher chance the model will not be able to learn it properly. So if you haven't watched what cost of dimensionality is and how we can be able to implement what exactly is a curse of dimensionality and how we can be able to identify that, then I'll request you to please go ahead and watch the video which has already been there in the channel for the curse of dimensionality. I will link it in the I button above and also in the description below for your reference. Alright, apart from curse of dimensionality, there also might be a chance of multicollinearity if we have features having high correlation. So what exactly is a multicollinearity? So although we will be discussing about multicollinearity in a greater detail when we will be discussing about linear regression and also the feature importance, but for the simplicity's sake, now what we can be able to understand multicollinearity is if we have two or three features which are having high correlation, means a correlation coefficient that comes around 0.8, 0.9 or 0.95, then those two features are actually same features or similar features. So impact of both the features to the model will be bad. So in that case, we have to treat the multicollinearity. So to treat the multicollinearity, we have two approaches, whether we can be able to drop one of those features which are having highly correlated, or else we can go ahead and combine both those features and make a single feature in replacement. So most of the cases, what we can be able to say that we try to remove the one feature which is having highly correlated, and in that way we can be able to avoid the multicollinearity problem. But in many cases, where business asks us that okay, these are the features which are being given to you are the features which are very important as in terms of business aspects, so we don't have the leverage to remove any of those features. In that case, what is going to be our approach? In that case, we have to deal with the multicollinearity for sure, and we can't be able to remove any of those features even if they are highly correlated. So in that case, one thing comes into the picture is like the dimensionality reduction technique, that is reducing those two dimensions or features into a single feature where we can be able to avoid the multicollinearity problem. So this is where principal component analysis or PCA comes into the picture. Okay, so as we got to know what exactly is PCA and what exactly is the work of the PCA, now we can be able to see how we can be able to implement the PCA in a practical aspect. Okay. Now here we are in the Jupyter notebook, the Google Collaboratory notebook. Let's try to implement principal component analysis from the scratch. So let's first import NumPy, Pandas and OS. Now let's load this data set, the data which is being there, data.csv. Let's load that data. Now let's understand this data. What exactly is data? So this is a data. For example, this is a data for let's say the number of people who are coming to a restaurant on a given date, what is the timestamp and what is the day of the week. Is this a weekend? Is this a holiday? What is the temperature outside? Is it a September or not? Is it during September, or is it a month? Is it an hour? Okay, in this way they have the feature. Okay, now let's see the head of the data set. Okay, so this is exactly the data set looks like. So here our y feature will be number of people, that is what is our target variable. Rest of all will be our x feature. So for the simplicity sake, let's remove the date, month and hour feature out of this, because that will be time constraint variables and we have to deal with these variables in a different way, like using pandas time frame and also using time delta. All of those approach we have to use, which we haven't discussed in this channel yet, so it will be a little confusing for us. So let's go ahead and remove these three features, that is date, month and hour. Okay, now we have removed the date, month and hour feature. Now let's see the data frame that we have. Okay, now it's perfect. Let's find out the correlation of the data set to understand how each and every individual feature which are being available are correlated with each other. So we can be able to see that day of the week and each weekend are 0.79 correlation coefficient, that is they are highly correlated. So let's go ahead and do the plotting of the correlation. Okay, now we have imported the matplotlib and the seaborn. So now we will be drawing the correlation graph. For that we have to decide the fixed size. Let's say 10 by 8. Now let's say SNS dot heat map, then df dot correlation, and we make it and not as true. And let's also change the color of the correlation plot that we will pick up the color named where it is. Also let's make the correlation coefficient rounded into 2 decimals so that it will be fitted properly into the heat map that we will be generating. Okay, so now plt dot title, a title correlation plot, and let's execute. Okay, we have a error. I did a mistake, so this should be figure. There's nothing in matplotlib called as fixed size. This is the fixed size, which is the inner template. Hopefully we have the matrix now. Yeah, we have got the matrix. As we can be able to see that we are having a high correlation in the green, 0.79 between the each weekend and the day of the week. Apart from that, no that much, no bigger correlation. We can be able to see from this color component that number of people and time staff have a correlation, higher correlation, but I think it is okay. Let's see how we can be able to deal with this using principal component analysis. Now, if we go ahead and do principal component analysis, there are few things that we have to do in terms of principal component analysis. So whenever we have any data set, the first thing first we have to do before applying principal component analysis is scale down the data into a single measuring unit. For that, we can be able to use either standard scaler or else min max scaler, whatever we prefer. Based on the scaling, we try to find, once the scaling is being done, so we have the data measured in a single measuring unit. Then what we try to do is like we then try to apply the principal component analysis on. So the basic idea of principal component analysis is we have to standardize or normalize the data first. Then we have to find out the correlation. This is what the background of the principal component analysis working. So this is how the principal component analysis is being done. So once we have standardized or normalized the data, then we pass it to the PCA, and what it does in the background is like it try to find out the correlation matrix. So whatever the correlation graph we are seeing, this is actually a matrix. Like, so how many number of features we have? 1 2 3 4 5 6 7 8 8. So 8 by 8 cross 8 matrix it will try to form. Based on that, it will try to find out, it will try to fit a it will try to fit the principal component analysis technique in terms of finding out the eigenvector and eigenvalue. And based on the eigenvalue, it actually tries to find out the eigenvector, and based on the eigenvector, it tries to find out the principal components. So the steps are like standardization or normalization of the data, then finding out the correlation of the data, then finding out the eigenvalues. On top of the eigenvalues, it actually find out the eigenvectors, and based on the eigenvectors, it actually finds out the principal components. So here we have already discussed in our channel before about the eigenvalue and eigenvector. If you haven't watched that video, I highly suggest you that go ahead and watch that video, so that you can be able to understand how PCA is exactly working, and you can be able to relate it over here whenever will be whatever we are talking right now. I'll link that one in the I button above and also in the description below. Okay, now let's go ahead and apply the principal component analysis. Now before applying principal component analysis or PCA, we have to divide the data into X and Y. So what is the Y for us over here? The number of people, that is the predictor value. So let's take the number of people as Y and X as tf.drop. Let's go ahead and standardize the data. For the standardization, we will be using standard scaler from the sklearn pre-processing. So let's import it. Now as we already know, we will be declaring a variable. Let's say scale is the variable name, which will be where we will assign the variable to the standard scaler. So we'll initialize the standard scaler in this way. Once this is being initialized, then we can do the fit transform to this. Let's name the data as x scaled. So once we have the data scaled, let's check it out. So this is what the matrix we have got in terms of scaling of the data. Now let's apply principal component analysis or PC on top of it. So let's import from sklearn dot decomposition import PCA. Now let's initialize PCA. So inside PCA there are a lot of parameters which are available. For now we are being concerned with the number of n components. So what this n component does is like we can be able to specify the number of principal components we want based on this feature. Number of features that we have specified, based on that we can be able to specify the number of components we want. If we don't specify the n components, so that means it takes it as none. In that case what it does, then number of features that we have, it actually forms the that number of principal components. But here we want, for example, let's say 4 number of principal components. So in that case what we can be able to do is like we can be able to specify the n components as 4. Before that, let's go ahead and check the number of features we have available under X. So X has 7 features. Now we are asking our principal component analysis or PCA to convert them into 4 features. Like these four features should contain all the important information and data, almost all the data that is being contained inside these 7 features. Okay, let's go ahead and do that. Once we have initialized principal component or PCA, then we do the fit transform on top of that. And what we will be fitting? The scale data that we have. Okay. Now this is what the principal component looks. Now on top of it, there is one thing that is now our principal component or PCA has been done. Now, how can we be able to know that whatever the PCA we found out, whatever the data that we have found out, we have converted these 7 features into these 4 features, right? So how can we be so sure that whatever the data we are getting over here, those are actually representing these 7 features? There should be a way to understand that how these 4 features are representing these 7 features. So yes, there is a way using which we can be able to do that. That is called as explained variance. So once we have fitted the principal component, so under this PCA we have a explained variance ratio which is being there, which actually tells us that how much the data that we have got from here is what is the representation of the data or in terms of the actual data. Like these 7 features, for example, these 7 features, whatever the information they are having, how much percentage of the information our principal components have captured. So that is what the explained variance ratio will tell us. So this is what the explained variance ratio. So that means the first principal component has got 25%, 25.72% of the data, the entire data. The second principal component has got 19.76% of the entire data. The third one got 15.23% of the entire data, and the fourth one has 14.11% of the entire data. Now let's draw a plot and understand how we can be able to see that how much percentage of this data are being covered using explained variance ratio. Now let's see how this explained variance is being printed. Okay, context it is, sorry. There is one more mistake that I have done. This underscore shouldn't be there. Yes, now it should work. Yeah, now it is working. We can be able to see that the first one is almost having 25% of the data, the second one is having almost 20% of the data, third one is having 15%, fourth one is having, let's say, 13%. So if we combine like 25 plus 20 plus 15 plus 13, then it will be around 45 plus 15 is 58, sorry, 60, 60 plus 13, that is 73. So now whatever the principal components that we have got, it is actually occupying this 70% of the total data, which is not what we want. We want it should occupy maximum of the data. So what we can be able to do now, we will do it using 5 principal components. So we will be implementing 5 principal components. So let's go ahead and copy this one. So here we're taking it as 5, and then what we are doing, then we will be fitting the data, fit transform. Okay, now we got the data. Now let's see the explained variance ratio. The explained variance ratio says this much of principal components we got. Okay, so what is the percentage? Let's see in graph, and then we will calculate. Okay, here we have the range which should be 5, not 4. The rest all will be same. Okay, now we can be able to see that how much percentage of the data we have covered of the entire total data. So 25 plus 2045 plus 1560 plus 1373, 73 plus 85% of the data. So here we can be able to see that we are almost getting the 85% of the coverage of the data, but still that is not the thing that we want. We at least want something which can be able to cover at more than 90 to 93% of the entire data. So what we will be doing, we will be doing the same experiment with the 6 number of components. Let's change it to 6, and rest all will be same. Like let's say let's do 6 principal components. Okay, now if you'll see, if we calculate how much percentage of the data it has covered, so it's 45, 1560, then it is 13 like 73, these are 12, 12, so it is 97. So it is now covering the 97 percentage of the data. So now we are satisfied. Okay, we can be able to take these 6 principal components and we can build the model on top of it. Now if you go ahead and see the exact correlation graph, there is an interesting thing to look after. We have only two features which are actually highly correlated. That is 0.79 is the high correlation. So we had, if we remove this number of feature, that is the output variable, then we have actually 7 variables available, and the principal components that we have got the optimal value is of 6 variables. That means we are actually making these two variables into a single variable. So if we do that, that means we are actually doing the same thing. So that means the principal components that is being formed are 6 number of features. So the features which are not highly correlated, the data will be there in a individual feature for them in the principal components. Alright, so this is it for this video. In the next video, we'll be discussing about the linear regression, what exactly is linear regression, and how we can be able to apply linear regression into the kind of data set that we are seeing. And then we will go ahead and discuss about the feature importance and also about the multi-collinearity problem. Until then, stay tuned and enjoy machine learning. Thank you.